All right, welcome back. What I want to talk about now is related rates. And I'm just going to start with a quick example of what I mean by related rates. I've got some point and it is moving along a curve. And I can identify the location of that point by giving you the x and y coordinates. But x is, as it moves along this curve, x is changing as a function of time, and y is changing as a function of time. And so what I now have is I have my two coordinates changing with time rather than changing with each other. They're related to each other because of time. So let's take a very quick example of what this might look like. Let's say that d is the distance of this point from the origin. I can very quickly draw myself a little slope triangle, and I know that that is the x value and that is the y value, again, as a function of time. X of t, x is a function of t, y is a function of t. So looking at this, I say, well, the distance of that point from the origin is the square root of x squared plus y squared. And I want to know how fast that distance is changing as a function of time. Now, because both x and y are functions of time, I should be able to use the chain rule and just take that derivative. So I've got 1/2 x squared plus y squared to the negative 1/2 times, so that's just the derivative of the square root function. Now here's where the chain rule comes into play. I need the derivative of x squared plus y squared. Well, the derivative of x squared is 2x, but with respect to time, the chain rule says multiply that by the change in x with respect to time, plus 2y times the rate of change of y with respect to time. I now have how fast that distance d is changing as a function of x, as a function of y, and as a function of the rates of change of both x and y with respect to time. Okay, let's do a quick example of how we would actually calculate something. So example 1, if you're using the same book that we're using, this is on page 252. But I want to know how the volume of a sphere is changing with respect to time if the radius is changing with respect to time. So first off, I know that the volume of a sphere is 4/3 pi r cubed. I know that r is a function of time. And so the rate of change of the volume with respect to time is 4/3 pi times the derivative of r cubed, which is 3r squared, times the rate of change of r with respect to time. Doing a little simplification, I get 4 pi r squared times the rate of change of r with respect to time. And I now know how the volume is changing relative to the radius changing, relative to an increasing or decreasing radius. Quick example number 2. I want to know the same thing relative to a cone. Volume is equal to pi over 3 r squared h for a cone, the radius squared times the height. And because I have a product here, I need to use the product rule. And I can very quickly find that the rate of change of volume with respect to time is pi over 3 times. Well, product rule says r squared times the derivative of h, remember, it's a function of time, plus h times the derivative of r, which is also a function of time. And there we go. And then I could reorganize and write it a little differently if I wanted to. But notice, that the change in volume as a function of time will depend on what is the radius right now, what is the height right now, and how fast are each of those two changing. All right, if you are in my class, go ahead and do exercise 2 in section 5.6, and we'll be back with more. Thanks for watching. Hope you learned something.